guys, this is a super late night chemistry video coming to you. I'm sorry it's coming so late. I'm sorry, this has been a super duper busy week for me. And I've been sick and my shoulder got hurt swimming on Monday. So it's been a heavy week for me. And I'm losing my voice, so that's another hard part of it. Sorry, it just keeps cutting out. And this has been kind of a hard chapter. It's some of it's a little bit new to me. I don't really remember doing it in high school chemistry. Probably I did, I guess. I don't know. It really doesn't. I don't really remember doing it. And I was talking to Mrs. Heaston Wednesday, and she mentioned that I'm going to get this wrong. Caitlin and Abby, your uncle or I think it's your uncle, not your grandpa, that made the comment that this book, some of the stuff that they do is definitely more like honors chemistry. And I would agree with that in this particular chapter. So let me just preface it though. Not making it sound really hard. It is, I think it's kind of a hard chapter. But what's not hard, really, the math is actually not hard at all. It's really a lot of adding and subtracting, actually. There's lots of good conceptual things going on in here, so you've got to read it. I'm just going to really give you an overview of the chapter. The book does do a good job of explaining things. There's just a lot of information. So, and I am super sleepy, so hopefully I can keep my brain working here to explain all this to you. So we're talking about thermodynamics. We talked about the first law of thermodynamics already, that energy is not created and energy is not lost, that the universe started with all the energy that there is, and none of it's lost or made. We don't make new energy. It just changes forms, right? And so now we're going to talk about enthalpy. That's a fun word to say. And enthalpy has to do with whether a reaction uses energy or needs some energy, requires energy for it to happen, or if it gives off energy. So if you remember when we talked about endothermic and exothermic, endothermic meaning that energy needed to be put into the system, exothermic meaning that energy was produced in the reaction. And so the book goes on to talk about how, my book and my camera's going to shift, maybe not. We start talking about that a lot more specifically in this chapter. And so they go on to talk about how we can kind of consider that if a reaction is endothermic, that energy is going into it, that the energy is sort of part of the reactants, versus if it's exothermic, we can consider energy as part of the product. Now, it's just a convention because we're not really when we have a chemical reaction, those reactants change and we get something else on the product side. We're not consuming that energy on that side, even though it's part of the reactant. So it's not exactly a reactant in that it can't be used up, but because it's used with the reactants, it's just a convention that's very convenient, and so we use it that way. So there's a good explanation of that. I think it's an adequate explanation in the book. And so then we can talk about the change in enthalpy, which again is, you'll see it as a triangle for change. And enthalpy is, it's like I'm speaking with a lisp. Enthalpy is abbreviated with an H, capital H. And so it's just the change in enthalpy is just the energy change that accompanies a chemical reaction. And so it can be negative or it can be positive. When the change in enthalpy is negative, that means that energy was produced, that it was exothermic. When it's positive, it means that energy was needed to be used. Just kind of to memorize that. Maybe it just intuitively makes sense to you. I don't think I finished that thought. If it's a positive change in enthalpy, then that means it's endothermic, that it was used to get the reactants needed energy to react. So hopefully that, maybe in some way that's intuitive too, and you'll just remember it. And if it's not, there's a handy dandy chart on page 451 that talks about that. They also talk about, so they say if the reaction is endothermic, the change in enthalpy is positive, heat is absorbed. That's pretty easy up until there. And then it says the potential energy stored in the reaction's products for endothermic is greater than the reactants. So there's more energy in the products, stored in the products' bonds. We'll get to that in a minute. When the reaction is exothermic, the change in enthalpy is negative. Heat is released, and the potential energy stored in the reaction's products is less than the reactants. So take a look at that. I'm not going to go through the examples because we will do that in class, and I might need a little more practice with them before I do it with you. Okay. What else is important on here? They do note, this is just a terminology thing, that chemists often, when they're referring to the change in enthalpy, they'll just call it enthalpy, and that is kind of a sloppy terminology, but it is used, so just to be aware of that, and so you don't get kind of jangled by that. Yeah, because enthalpy is just the energy associated with a particular substance. The change in enthalpy is how the energy change that happens in a particular equation. So, okay. Like the enthalpy would be that amount of energy that's needed to get the equation to happen, or the energy that's given off, but that change is the difference in that. Okay, let's see. Then they go through an experiment we might do this experiment, I'm not sure yet, but you can certainly take a look at it, and they show how they figure out the change in enthalpy by experiment, by using a chemical reaction to determine change in enthalpy. So read through that because it is helpful. Then they talk about how the change in enthalpy can be determined by bond energies. So if you look at it's helpful to look at the pictures as you're listening to this on page 455. Excuse me. They show a reaction about the burning of methane. So we know combustion is our fuel plus oxygen gives us either carbon dioxide, carbon monoxide plus water. So that's just showing that equation. And then they make the Lewis structures for each of those. And so we see the carbon with 4 hydrogen bonded around the sides, and we see oxygen, these O2 molecules, they share a double bond. And then we see how those bonds change. And so we can actually, let me pause. I was getting ahead of myself. As they say in here, what makes sense maybe to you is that if you have to break bonds on one side, that might require energy. I mean, think if you have to break something, like physically, even to break something, it requires the energy of your hands. So if you have to break bonds, that requires energy. But what may not make as much sense, but is nevertheless true, and I've kind of struggled with this concept. I'm having a hard time with it in my brain, so I just kind of had to accept it until it makes a little more sense to me. But when bonds are formed on the product side of the equation, energy is released. I've been trying to find something that might explain that. I'd like to search through Khan Academy and see if Sal makes some explanation of that. I was looking at the topic of thermodynamics on Khan Academy, and it seemed really, really complicated. So I was actually going to just throw some of those videos up for you, but I think it'll be more confusing as a start. So I'll search for this specifically, but at least for the meantime, just know that when the bonds are formed over on that product side, the energy is actually released. So their point is that energy is being absorbed and released throughout a chemical reaction because, right, bonds are breaking, bonds are forming. But the question is, what is the overall net absorption and release? So if there's a greater release and less, like if you've got really weak bonds and it doesn't take very much energy to break them, but you have really strong bonds over on the product side, so a lot of energy is released to make those, then you're gonna have more energy on the product side, so you're gonna have an exothermic. Or on the reactant side, if you have really strong bonds and it takes a lot of energy to break those, but really weak bonds on the product side, it's not very much energy is going to be released when those bonds are made, so you're going to have an endothermic reaction. Hopefully that makes sense. So you've heard it, read it, and try to see if you can get that to kind of roll around in your brain. Okay, so that's what they're talking about here. So then they give us actually some bond energies, something more specific instead of just that qualitative description I gave. They gave us a chart of some bond energies. Obviously do not have to memorize this. There are a whole bunch of charts in this chapter, and what you just need to know is how to use them, the information from them, but you'll have them for the test. No memorizations of these random numbers that are in these charts. They're not random numbers, but they would be random if you're trying to memorize them. So table 13.2 on page 456, they give us bond energies. And so what we can do is look at something like example 13.2, where they give us nitrogen plus hydrogen gives us ammonium. That's ammonium, isn't it? Yes, ammonia rather. And so we can look at like those bonds. We're going to do this in class, but we can look at the bonds between the nitrogen and the hydrogen and the ammonium, and we can add up one side and subtract the other side and see what the difference is to see if it's negative or positive. So this involves writing Lewis structures. We're going to actually learn a method where we don't have to write the Lewis structures, but they do have you practice this. And you'll look at this example maybe, hopefully, and see that it's really long, but it's actually not too hard. They're just giving a lot of description as they do it. And so in that particular example, we end up with a negative 78 kilojoules. So if you remember, it's negative. That means it's exothermic. So that means that there was more energy being released and those bonds being created on the product side in that particular, and that's coming from those bond energies from the table. So we'll work that example so that makes sense. But that's what's happening there. Then, where do we get to? Hess's law. Let's see here. Hess's law. I'm trying to remember what this was. Oh, this is yes, this whole section was kind of crazy. So when they start talking about Hess's law, they preface it and say there's a whole bunch of stuff going on in this section, and your ability to understand it is not necessarily going to be indicative of your ability to actually work the problems. I would agree with that. So read about Hess's law. It talks about enthalpy being a state function. A state function meaning that, let's see. I need to refresh my brain on this one. This was new to me. I'll just read the definition. A state function is any quantity that depends solely on the final destination, not on the way to get to that destination. So first they give an example about like bush gardens. I don't know why they pick bush gardens. Maybe they're from Florida, or maybe they're from wherever that's at. I was going to say Florida. They must have them in different places. There's one in Florida too. They're talking about Virginia. The fact that there's lots of different ways to get there, but once you get there, most people have a day that's fun. So the state function is that they have a day that's fun, but how they got there was different. It's a pretty good analogy. Then they show you in chemistry 2 different ways to make water. They have 2H2 plus O2 gives you 2H2O, or 2H2O2 gives you 2H2O plus O2. So in either case, you made water, but you got to it 2 different ways. There's a lot of 2's in those sentences. So look at that on 461 as we're talking about. That will help. So that's just explaining that what a state function is, and that enthalpy, Hess's law just says that enthalpy is a state function. And so given that, sorry, I'm going to have to refresh my memory on this part. Look at the example. Let me pause this before I keep talking. So I'm trying to remember this section. I'm going to pause this. Hold on. I'm going to stop it and start recording again.